This is the first lesson of Unit 9, Lines and Planes. In this lesson, we're going to look at vector and parametric equations of a line and a plane. So let's start with vector equations. The equation of a line can be anything that states the conditions that all points on the line must meet. So for example, we've seen before, y is equal to 6x plus 5, so y is equal to mx plus b. This right here is an equation where you can input an x value and you will get a y value on that line. Equations of lines, written like the one above, are called scalar or Cartesian equations. We can also write the equation of a line using vectors. For these vector equations, we need two pieces of information. The position of a known point on the line, P naught, and a direction vector, which can be any vector in the direction of the line. Let's start by examining direction vectors, D. Write a direction vector D for the following example. So the line that passes through points 3, 4, and 7, 2. So if I want a vector that passes through those points, that will give me the direction of the line. So I'll write a direction vector that is as follows. So the direction vector in this case is going to be equal to vector CD. And so CD is equal to the position vector from the origin to D minus the position vector from the origin to point C. So CD in this case is equal to 7, 2 minus 3, 4, and we get 4, -2. So therefore the direction vector of this line is 4, -2. This will give us the direction the line heads in. If a line has slope -5/3, then -5 just represents the rise and -3 represents the run. Well, this means therefore the rise is essentially just -5 times the unit vector in the y direction, and the run is just 3 times the unit vector in the x direction. So I have the components of the x component and the y component of this direction vector. So I can say, therefore, the direction vector is simply 3, the x component, and -5, the y component. A vertical line passing through -6, 5. Well, we have to think ourselves like, what is the direction of a vertical line? What is direction of vertical line? Well, remember, all I'm looking for here is just a direction vector of a vertical line, and you'll notice, or you'll note, that the direction vector of a vertical line is simply just 0, 1, which is the same as j cap, because j cap is the unit vector in the y direction, which is vertical. Now, let's write a vector equation for the line with a slope 1/2 that passes through point P naught 3, 4. So if I have slope 1/2, I have to recall that this is my rise, and this right here is my run. So my rise is my y component, and my run is my x component of the direction vector. So D is equal to 2, 1. So I have the direction vector. And so now I'm going to place the direction vector on this line. Okay, so this right here is my direction vector 2, 1. But recall though that we can't define a line just in terms of the direction vector, because a line is fixed in space and a vector is not, because if a vector preserves its magnitude and direction, then you can move it about in 2D space. So a direction vector in and of itself does not define the equation of a line. All it does is it gives us essentially the slope of the line. However, it does pass through this point 3, 4. So what I'm going to do right here is I'm going to put this point right here, 3, 4. In fact, what I might do here is I might even just move it so that it's over here. 1 second. Okay, there we go. So I have the point and I have the direction vector right here. So what I'd like to do is I'd like to create another point right here, and my other point is going to be, this is going to be P1, and that's going to be 5, 5. Okay, so that's also a point on the line. All right, so if I want to get to this point right here, then I can't just use the direction vector. What I need to do is I need to have a vector that goes from the origin to the original point stated, P0, 3, 4. Because if I can take this vector here plus the resultant vector, then I can have a vector that points at the equation or points at the point on the line. So I am taking my OP0, so this one right here is my OP0, taking my OP0 vector, which is from the origin to a known point on the line, plus the direction vector, which gives me the slope, and the resultant will point to the xy value on the line. Okay, and so this right here, this line represents, or this vector represents OP1. So OP1 is equal to 5, 5. Well, how did we get that? Well, OP1 was achieved by taking OP0 plus the direction vector, now multiplied by some scalar value, right? I don't know how big the direction vector needed to be, what the magnitude of that direction vector needed to be to get to 5, 5, but we can actually find that out, okay? So OP sub 1 is 5, 5, okay? It's 5, 5, right? That's a point on the line. And that position vector, which points to a point on the line, was the sum of the position vector from the origin to a known point or a given point on the line, so that was 3, 4, plus some scalar value times the direction vector, which I already had stated was 2, 1. Okay, and so now what we can do is we can actually determine what the value is, right? So that means that 5 had to be equal to, so the x value had to be equal to 3 plus 2 times t. So 5 is equal to 3 plus 2, well, t has to be 1. Okay, so t had to be 1. And let's just double check. The y component is also 5, and that's 4 plus some value of t, yeah, t is equal to 1. Okay, so in order to get to 5, 5, t had to be 1. Let's point to a different point on the line. And so let's now point to -1, 2. All right, so I'm going to take a point and go -1, 2, and that's my point 2. So we'll say, like, I don't know, say right here. Okay, so that right there is 0.2, and it's -1, 2. All right, I'm just, for the sake of clarity, I'm going to delete this position vector right here. Okay, so just give me a second. Okay, so we can see that my original position vector to a point on the line, that can stay, but something has to happen with my direction vector if I want to get to this point on the line. Well, you might be able to see that the direction vector, not only does it have to change direction, but it also has to increase in magnitude. So what has to happen to this is that it has to change direction and it has to increase in magnitude to get to this point right there. So let's just change that right there. Okay, so that is what needs to happen to arrive at another resultant that points to another point on the line. So you can see that these vector equations are essentially just the sum of an original position vector plus the direction vector times some scalar will get you to any point defined on this line. Let's figure out what this was. Let's figure out what the t value was in this case. So -1, 2 is equal to my original point, and then I had to take my direction vector and multiply it by some scalar t. Well, you can think right here, 3 plus 2t has to be equal to -1. So let's write that right there. 3 plus 2t has to be equal to -1. So 2t is equal to -4 by bringing in the 3 to the over side. And so t had to be equal to -2. And that seems to track because we flipped the direction of the direction vector, right? It's now going in the opposite direction, so it's negative. And the magnitude had to increase. But let's just double check with our y component as well. So 2 is equal to 3 plus t. And let's see if this 2, sorry, apologies, that should say 4. 4 plus t, and then so then -2 is equal to t, and yeah, that checks out right there. Okay, we're not going to do a third point right here, so let's just actually just delete this right here, or you can just cross it out. Okay, so we can define any point on this line. So any xy value, we can get a vector that points to any xy value on this line, right? We can get one of these position vectors that points to any xy value on this line by taking that original position vector, which was 3, 4, so that was the given point, plus t times its direction vector. Okay, and so we can also say this, xy is equal to OP naught plus t times the direction vector, where t is an element of all real numbers, some scalar value of t. Okay, let's keep going here. So in general, the vector equation of a line is given by OP, so the origin to any point on the line is the origin to a given point on the line, plus t, some scalar value, times the direction vector, where t is an element of real numbers. This works in 3 space as it does in 2 space. Okay, so where OP represents the position vector to any point on the line, OP represents the position vector to the initial point on the line, and TD represents the direction vector multiplied by some scalar t. Okay, so now that we have the theory laid out, we can hopefully move a little quicker through the rest of this material. Okay, so state a vector equation of a line that passes through these points. And so what we'll do is the first thing, we've got 2 points on the line. We want the vector equation. Well, if I have 2 points on the line, I can find slope. But in vector equations, we don't find slope. What we do is we find the direction vector. So let's find the direction vector, which is PQ. Okay, and so PQ is equal to, we'll just say right here, 7 minus 4. So OQ minus OP, so 7 minus 4, -5 minus 1. And then I should get right here 3, -6. So that's my direction vector. So now that I have the direction vector and I have a point on the line, I can create my equation of line. So OP, so the origin to any point on the line, is a point. So the origin to any point, so 4, 1, plus t times the direction vector, which is 3, negative 6. So this works as a vector equation of the line. But it doesn't need to be necessarily 4, 1. I could have also have said 7, negative 5, because that is a point on the line, plus t times the direction vector. Notice that the direction vector does not change because that is the slope of the line. So either of those work in this question. State two other points on this line. So to state two other points on this line, what I'll do is I'm not going to state two. I'll just say let's just state one other point. To generate points on the line, I just select values for t. Okay, so select values for t, and that will generate other points on this line. So let's say, for example, set t equal to 3. Well, if t is equal to 3, then x is equal to, so my x values, so if we want to say right here, this is xy, okay, x would be equal to, right, or you can do xy here, okay, x would be equal to 4 plus 3 times 3. So the t value is 3 times 3. So then x is equal to 4 plus 9. So x is equal to 13. And the y value, right, would be 1 plus 3 times negative 6. So 1 plus 3 times negative 6. So y is equal to 1 minus 18. And y is equal to negative 17. So 13, negative 17 would be a point on that line. Okay, so all we did there is we just set values for t, and then we looked at the components and added them up. So so 13, negative 7 is a point on the line. Okay, if you wanted to do another one, you could just say set t is equal to 1. You don't have to necessarily break it up this way. What you could say is OP is equal to 4 comma 1 plus 1, 3, negative 6. So instead of breaking it up into its original components or its individual components there, we can just say it like this. Okay, so 4 plus 3, that's going to be 7. And then 1 plus negative 6. Well, 1 plus negative 6 is going to be 5. So 7, 5 works here. Okay. It says, can you simplify and reduce the direction vector? Absolutely, you can. So 3, negative 6 could have easily simplified into 1, negative 2, and that works. Okay, so that could have been the direction vector as well if you wanted to, but it's fine to keep it as 3, comma, negative 6. It doesn't change. It will continue to generate points on the line. Okay, so we're now going to move into parametric equations of the line, and we've kind of got a taste for it up here by separating it into its components, but let's just see what it says. Okay, parametric equations are modifications of vector equations written separately in terms of x and y rather than a single equation. So state the parametric equations of the line OP is equal to 3, 4 plus t 2 comma 1. Okay, so what I'll do right there is I'll say, well, OP is the origin to any point on the line, so xy is equal to 3 comma 4 plus t 2 comma 1, right? I'll distribute the t in because it is a scalar. Okay, so I'll distribute that in. And so I can say that xy is simply equal to 3 comma 4 plus 2t t, right? So then I can separate them into the parametric equations. So I'll just write right here, parametric equations. So then I'll say x is equal to 3 plus 2t, and then y is equal to 4 plus t. Okay, and again, where t is an element of all real numbers. Okay, what point on the line corresponds to the parameter value of t is equal to 3? Okay, so we just basically set t is equal to 3, and then therefore x is equal to 3 plus 2 times 3, so x is equal to 9. Y is equal to 4 plus 3, so y is equal to 7. So therefore 0.97 is the point on the line when t is equal to 3. Okay, next question says, does the point 1, -8 lie on this line? So if I pick a value for t, will a single value of t give me 1 for x, and will the same value of t, will that give me -8 for y? Let's check. Okay, so what I'm going to do is I'm going to set x is equal to 1. So therefore 1 is equal to 3 plus 2t. I'm using the x parametric equation. So then -2, by bringing the 3 over, -2 is equal to 2t, and therefore t is equal to -1. So for x to equal to 1, t had to be equal to -1. Well, if y is equal to -8, then t should also have to be -1 if this is a point on the line. But let's check. Set y is equal to -8. So y equal to -8, so therefore -8 is equal to 4 plus t, and -12 is equal to t. Well, that's not what it should be, because to get a point on the line, you should have, as we had up here, to get a point on the line, a single value for t. A single scalar multiplier should be able to generate the point on the line. In this case, that did not happen. So what we'll do is I'll do a line here, and I'll do a line here, and I'll say, since no single t value can generate this point, it does not exist on the line. Okay, moving right along. We've just got about 5 more examples, but we'll try and get through them a little quickly. Okay, find the point on the given line where y coordinate is 3 times the x coordinate. So I'm going to give you a vector equation here. Okay, so this is the vector equation. Okay, and the vector equation is OP is equal to 3, 4 plus t 2, 1. So find the point on this line where the y coordinate is 3 times the x coordinate. So let's separate these into its parametric equations. So that's my vector equation. My parametric equations are as follows. X is equal to 3 plus 2t. So the equation for the x component, and now the equation for the y component is 4 plus t. Okay, again, this is for t is an element of real numbers. So for t element of all real numbers. Okay. The thing that I know though is that the y coordinate is 3 times the x component. So I'll say, but y is equal to 3x. So therefore, instead of writing y, I'll just say 3x is equal to 4 plus t. So let me put these equations together. Okay, so this is one equation, that's one parametric equation, that's my second parametric equation, and this became my second parametric equation because I'm looking for the case in which y is equal to 3x. So let's put them on top of each other. X is equal to 3 plus 2t, and then my second parametric equation is 3x is equal to 4 plus t. So two equations, two unknowns. What I'm going to do here is I'm going to use the elimination method, if only because this is something that you might experience later if you do linear algebra, but in the purposes or in the context of matrices. So x is equal to 3 plus 2t, and I'll see 6x is equal to 8 plus 2t. Okay, and now what I'll do is I'll subtract these two equations. And so x minus 6x is negative 5x. 3 minus 8 is negative 5, and 2t minus 2t is equal to 0. So then x is equal to 1. All right. So if I have x is equal to 1, so if x is equal to 1, then what I'll say is y is equal to 3 times 1, and so y is equal to 3. So therefore, 1, 3 is the point on the line where y is 3 times the x value. Okay, find the x and y intercepts of OP given this right here. Again, what I'll do is I will set up my parametric equations. So therefore, x is equal to 4 plus negative 5t, or what we can say is just x is equal to 4 minus 5t, and then y is equal to negative 2 plus t. Okay, so I've got my parametric equations for x and for y. So if I want to find the x-intercept, okay, so I'll do a title over here, x-intercept. If I want to find my x-intercept, I set y equal to 0. So therefore, I'll take the parametric equation for y, and I'll set that equal to 0, negative 2 plus t. So 2 is equal to t. So when y is equal to 0, t has to be 2. And so therefore, sub t is equal to 2 into my x parametric equation. X is equal to 4 minus 5 times 2. X is equal to 4 minus 10. X is equal to negative 6. So therefore, negative 6, 0 is the x-intercept. Same thing for y-intercept. What I'm going to do is I'm going to set x is equal to 0. So therefore, 0 is equal to 4 minus 5t. So therefore, 4 over 5 is equal to t. So 4 over 5 has to be the value of t to cause x to be equal to 0, which is what I need for the y-intercept. So then y is equal to negative 2 plus 4 over 5. And so then y is equal to negative 6 over 5. So therefore, 0, negative 6 over 5 is the y-intercept. Okay, determine if the lines are parallel or perpendicular or neither. So what I have right here is I have my parametric equations. And so what I'm going to do is I am going to find the vector equations of these two lines. So literally I'm going to write that out. So find the vector equations of the two lines. Okay. So this right here represents line 1. So line 1, any x, y value on line 1 could be defined as 4 and 0 plus t, negative 3, 5. Okay, and so you can see that x is equal to 4 plus negative 3t, and y would be equal to 0 plus 5t. That works out. Let me find the vector equation of the second line. X, y is equal to, in this case right here, it's also 4, comma 0 plus s, that's my parameter s, and then over here, negative 5, negative 3. So you may have noticed that this right here is my direction vector for 1, and this right here is my direction vector for 2. Okay, so I'll start with perpendicular. Okay, if L1 is perpendicular to L2, then, so if these two lines are perpendicular, then the dot product of their direction vectors should equal to 0, right? If the lines are perpendicular, then the direction vectors are perpendicular, and so therefore the dot product of those two lines should be equal to 0. So let's check this. So let's check D1, D2. Okay, so D1 was given as negative 3, comma 5 dot, and D2 is given as negative 5, negative 3. Okay, and so that's going to be equal to negative 3, negative 5 plus 5 times negative 3. And you can see that that equals to 0. So therefore, L1 is perpendicular to L2. Okay, so we don't need to do the rest of it because we've discovered that it is in fact perpendicular. Okay, another one where we have to determine if the lines are parallel or perpendicular. And this is already kind of nice because we already have the direction vectors of the two lines, right? So what we'll do is we'll check the dot product of the two direction vectors. Okay. So then 3 comma 4 dot -6 -8 is equal to 3 times -6 plus 4 times -8. And so that should be equal to -50. Okay, so therefore not perpendicular. Okay. And so what we'll do is we'll do the check if they're parallel. Okay. So if line 1 is parallel to line 2, then the direction vector of 1 is going to be some scalar multiple of the direction vector 2. That's how we showed parallel vectors in the previous unit. And it works for lines as well. If lines are parallel, then their direction vectors are parallel, right? Or 1 is just a scalar multiple of the other. Okay, so let's look at direction vector 1. So 3 comma 4, right, is equal to k -6 -8, right? So this would mean, therefore, k is equal to -1/2. Okay. So let's check. K times -1/2 gives me 3, and k times -1/2 gives me 4. So therefore, line 1 is parallel to line 2 because there is a scalar multiple of this direction vector that can produce this vector right there. Okay, moving on to the last problem right here. Find the intersection of OP1 and OP2, where OP is the vector equation of the first line and OP2 is the vector equation of the second line. Okay, so what I'm just going to quickly do here is I'm going to find the parametric equations of each of these lines. So the parametric equation of line 1 is x is equal to 9 plus 2t, and y is equal to 4 minus t. And then this one is x is equal to -2 plus s, and y is equal to 6 plus 3s. All right, and so you may recall from grade 10 that if lines intersect, then they share the same x, y point. So there's some point x, y that lies on both of these lines if they intersect. Okay, so what I'll do right here is what I'm going to do is I'm going to set the x value of this parametric equation to the x value of this parametric equation. So therefore, 9 plus 2t is equal to -2 plus s. And then I'll set the y value of this parametric equation to the y value of this parametric equation. So 4 minus t is equal to 6 plus 3s. And so I have two equations, two unknowns. I'm going to solve this using elimination. So I'm going to take the first one, I'm going to multiply that by 3. Okay. So then I get 27 plus 6t is equal to -6 plus 3s. And then I'll get 4 minus t is equal to 6 plus 3s. And now I can subtract those two equations. And subtracting those two equations yields 23 plus 7t is equal to -12 plus, and if I subtract that, that's 0. Okay. So 35 is equal to negative 7t. So then negative 5 is equal to t. Okay, so what I'll say right here is, therefore, the point of intersection happens when t is equal to negative 5. And you might be wondering, well, don't I need to find what s is? Well, no, if we know that t is equal to negative 5, that's going to generate an xy point that is the same as this xy point because we equated them to say that they are sharing that point. So then all I do is I sub t equals to negative 5 into line 1. Okay, so x is equal to 9 plus 2 times negative 5. X is equal to negative 1. And then y is equal to 4 minus negative 5. So y is equal to 9. So therefore, negative 1, 9 is the point of intersection. Okay, so I know that was a bit of a longer video, but that really does cover the bulk of equations, vector equations and parametric equations. Thanks for watching.